Hello, Calculus AB students. I hope that you're having a great break and are very excited to watch this brand new calculus video. Just a great way to spend your fall break, I know. Before I get started with our new notes, I just wanted to touch base on all of the theorems that we've learned so far in Chapter 4 and kind of remind you of the purpose of those theorems. So the first one that we delved into was the extreme value theorem. So the extreme value theorem, the purpose of this, underneath I'm just going to write the purpose, is to prove that extreme max and mins exist. With this theorem, you don't even have to tell me what they are. It just tells you, yes, there will be an extreme max, there will be an extreme minimum. Pretty simple. The next one we touched base on was blah, 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 blah. Where's the extreme value theorem? Or the mean value theorem? Oh yeah, Rolle's theorem. And Rolle's theorem, the whole purpose of this thing is just to prove that if you have the starting point and the ending point at the same place, the purpose here is to prove there's a point, where f prime of c equals 0. So the whole purpose here is to just prove that the derivative equals 0 at some point. And a trick that some people teach is Rolle's theorem looks a lot like Rolly. So it's kind of like rolling over the hill. At some point when you're rolling over this hill, the slope is going to turn to 0. Rolling over the hill, slope is 0 there. What else we got? Mean value theorem. This is the whole purpose of this is to prove the instantaneous slope equals the average slope at some point C. So this is where you'll have to use the mean value theorem when you're asked to prove that there's a specific value for the slope. So then you can find the average slope at a certain point and prove that at some point it will equal that. And then there's one last one that we have learned, and this is the first derivative test. The purpose of the first derivative test here is to find relative extrema using the first derivative. Okay. So this will just help you find local maximum and minimum using the first derivative. So observing where is the function increasing, where is it decreasing, will that give you a maximum or a minimum? The next theorem, the new theorem that we're going to be learning in our notes, is very similar to that one. It is called the second derivative test. So the second derivative test, it still is for relative extrema. So the purpose here is still looking for local maximum and minimum, but we're going to be using the second derivative in order to determine that. So what this says is if we have a function f such that x equals c, and c is a critical value, and remember critical values occur when the first derivatives equal 0. And then the second derivative exists on an open interval containing c. Then if the second derivative at c is greater than 0, then c of f of c is a relative minimum. If the second derivative at c is less than 0, then c is a relative maximum. And if the second derivative at c equals 0, then this test fails and we have to use the first derivative. So if we ever get something equal to 0, then you have to revert back to the first derivative to figure out, is it going to be a max or is it going to be a minimum? Both of these tests work. So the first derivative test and the second derivative test will give you the same responses no matter which one you use. Okay, they're both going to work out the same way. It's just two different ways to find relative extrema on an interval. Let's look at an example. Example 6 says, find the coordinates of the relative extrema for this function. Justify, if possible, using the first and second derivative test. Sketch the graph. So we'll use the second derivative test for this one. So second derivative test means we have to find the second derivative and then see if at that critical point the second derivative is positive or negative, and that will tell us whether it's a minimum or a maximum. So let's start by taking the derivatives. So f prime of x equals negative 15x to the 4th power plus 15x squared. Oh, sorry. I said let's find the second derivative. However, this theorem tells us that we want to find the critical points. Okay? So in order to find a critical points, and I specifically underline this, the critical points are the values where f prime of c equals 0. So we're just going to use this first derivative to find the critical points. My bad. So there's my first derivative. Set it equal to 0. And to find the critical points, we're going to factor. So let's take out negative 15x squared. I'm left with x squared plus or minus 1 equals 0. This will give me x equals 0 and x equals plus or minus 1. These are my critical values. I have 3 of them. So now I'm going to take these critical values and plug them into the second derivative. So at this point I will find the second derivative and plug my critical values in and see what's happening at those points. So let's find the second derivative now. F double prime of x will be negative 60x cubed plus 30x. Okay. Plug in my critical values. F double prime of 1, f double prime negative 1, f double prime 0. So f double prime of 1 is going to equal negative 30. Since this is a negative number, let's look back up at our rules. When you plug it in and you get a negative number, that means that f of c is a relative maximum. So we can say that this point, 1, negative 30, is a relative maximum. Okay. When we plug in negative 1, we get 60 minus 30 equals 30. This is a positive number. So we're going to get that. Oh, Miss Patterson made another mistake. Oh my. Ay, ay, ay. Let's look at this test. It shows us that c and f of c. Doi. So we need to figure out what f of c is, which is very simple. We just plug it back into my original function. Okay. So instead of 1 and negative 30, we're going to look at 1 and f of 1. And 1 f of 1 is going to be 1, plug it into f, and you get 2. So 1, 2 is relative max, And then here, negative 1, f of negative 1 is going to be a relative min. Negative 1, f of negative 1, plug that back into your original function, and we get negative 1, negative 2. That point is a relative minimum. I want to talk real quick about how I recognized that I was making an error, because it's always important as you're going through problems to realize when something isn't quite making sense. So as I was writing that these were relative max and relative min, I noticed that I had 1 negative 30 was a relative max, and then negative 1 positive 30 was a relative min, which simply doesn't really make sense. Look at these y values. So as I was writing that down, I was thinking, something's not quite right, so I went back and checked what I was doing. Okay. And then this last one. So if we plug in 0 to f prime, or f double prime, then we get 0. Uh-oh, what happens when you plug a critical value into the second derivative and you get 0? The test fails. Well, the second derivative test fails. And what should we do? Try the first derivative test. So remember the first derivative test was when we made a little chart like this, with 0 marked on it, and we plugged different values into f prime. So this chart for the first derivative test uses f prime. And we're going to be plugging these values into this equation up here. So we can try negative 1. We plug negative 1 into this function. Oh yeah, we can't plug negative 1. So we need to plug in like negative 0.5. If we plug negative 0.5 into that first derivative, then we get a negative value. And if we plug positive 0.5 into f prime, then we also get a negative value. Okay. So using the first derivative test, we're able to kind of see why that second derivative test failed. Since they're both negative there is neither a max nor a min. And we still have a critical value there. This is a scenario where it perhaps it looks like a cubic, except in this case it is more than upside down cubic like that. There's still a critical value there, but it doesn't change from a max to a min in this case. So we're able to find a relative max and a relative factor, even though there were 3 critical values. If we were to try to sketch this thing, so we have these 2 different points that we could graph on here real quick. We have a relative max at 1, 2, and a min at negative 1, negative 2. And here, at 0, 0, we're going to have kind of a turning point. So this graph probably looks something like this. This is a cubic. Alright. These next problems are pretty interesting. We're not given an equation. This is how we're going to determine graphically. Just looking at a graph of y equals f prime. We're given a graph of the derivative. We have to figure out what the original function looks like. remember that points are increasing when f prime of x is greater than 0. It's going to be decreasing where f prime of x is less than 0. So we're given f prime. It's really easy to see where it's greater than or less than 0. You just have to look to see where it's above or below this x-axis. So this is, I don't really know why they split A and B into two, to be honest. points of inflection occur when you change from crunching up to crunching down. So wherever the concavity changes, the points of inflection, concavity is changing at x equals 2, 3, 5, and 7. So they're going to be like turning points down. first derivative. So let's look at the first derivative. S prime of x equals, oh yay, a fractional equal. So before I do it, you remember this is where we get those funky factoring. This is funky factoring here. Before I write it down, try to guess what I'm going to factor out. What might I factor out? assume that f of 0 equals 0 at the point on here, we can actually find the starting point. So I can plug 0 into the original equation I was given to find the next starting point. And I end up getting 0. So I do have the point 0, 0 on this graph. That's my starting point. I also want to make sure to include 1 because that's my inflection point, and I want to include 8 because that's where I change from decreasing to increasing. So I have a minimum of x equals 8. I know that here I'm increasing before I get to 0, and I'm concave down, and then I'm decreasing all the way to I think there's concave down and increasing. I start decreasing and still concave down until I get to my inflection point of 1. Concave down all the way to here, and then for the rest of the interval, I'll pass 1 and concave up for the rest of my graph. So it's going to be like a smile that's decreasing until I get to 8. And 8 is my minimum, and then I start increasing. It's going to keep going like that. Smile for the rest of the graph. One way we can check our work here, we're given the original equation. Go ahead, plug the original equation in your graphing calculators. Check to see if you did it right. Or decimal, whatever you want. And when you do, you'll figure out, whoa, our graph looks beautiful. It's exactly what it looks like on my graphing calculator. That's me as the Windows person. That's okay. But in general, got the correct shape. So that's exactly what I